Flux density homework, problem 3. Let's go to it. We got a volume charge density located in free space. It's given as rho v, or volume charge density, equals to 2 times E at minus 1000 R nanocoulombs per cubic meters. And it's contained for a radius that goes from 0 to 1 millimeters. And we will have another charge density of 0 elsewhere. What does it mean? Now, free clue to start understanding this problem. If we look at the variables present in the charge distribution, we will see that we work with R. We see we have R value that goes from 0 to R to 1. That means we're working with spherical coordinates. If we're working with the spherical coordinates, it's fair to say that we will work with an sphere. And a sphere that will look kind of like this. Now, even if it is badly drawn, will give us an idea of how to start analyzing the problem. The best thing to do is consider that our sphere, its center at the origin, z-axis, x-axis, and y-axis, like that. So we got the sphere center at the origin as shown in here. If that's the case, well, we can say that we will have a charge that will correspond to this distribution. Always my radius goes from 0 to any side of the sphere. That means when my radius reaches to 1 millimeter. Always I don't go outside this range, we will have this charge distribution. If we go beyond that 1 millimeter at any direction, our rho b is going to be equal to 0 coulombs per cubic meters. Again, if we work within this range from 0 to 1 millimeter, we will have a rho b equals to 2 times e at minus 1000 radius nanocoulombs per cubic meters. If we go outside that range, we will have a rho b equal to 0. That means we have our charge contained within that sphere, just like in the picture, just like that. Now, the problem is asking me two things. First, find the total charge enclosed by the spherical surface of one radius equals to 1 millimeter. That means I want to know what's going to be the charge containing in here, in a sphere surface of 1 millimeter. So we can calculate that by the assumption that charge equals to rho v times volume, or more accurately, that charge equals to volume integration of rho v dv. That's for the first part. For the second part, by using Gauss' law, calculate the value of the flux density on the surface of radius equals to 1 millimeter. So we first calculate what's going to be the total charge inside given by this volume distribution, and then we calculate the flux density. So let's go to it. Some important things to consider before we start. First, the d volume of a sphere is going to be given as radius squared sine of theta d radius d theta d phi. Once again, theta is going to give me my value that goes, or my angle that goes up and down. So it will have limits from 0 to pi. Phi, it's going to give me the angle that goes all the way around. It will have limits from 0 to 2 pi. And the radius is going to be the extension of my sphere. In this case, it's going to go from 0 to 1 millimeter. That 1 millimeter is better expressed as 0.001 meter for the radius. So if we start substituting these values, we will see that the charge is going to be equal to the triple integral for radius, theta, and phi of the expression 2 times E at minus 1000 R the volume. However, that the volume is substituted by this, which is radius squared sine of theta d radius d theta d phi. We set the limits. Radius from 0 to 0.001. Theta from 0 to pi. Phi from 0 to 2 pi. And we start integrating by the easiest. And to see how we can actually simplify stuff. First, this 2 is constant. It can go out. Second, we're working with nanocolumns, so we can rewrite this as Q equals to 2 times 10 at minus 9, that's giving me the nanocolumns, times the integration 0, 0.001, 0 to pi, 0 on 2 pi of E at minus 10, 1000 radius, R squared, sine of theta, dr, d theta, d phi. Now, the easiest way to start integrating, we start with the phi. We don't have any phi variable. So we integrate phi from 0 to 2 pi. That's going to deliver phi evaluated from 0 to 2 pi. So Q equals 2 times 10 at minus 9 phi evaluated from 0 on 2 pi. This is going to deliver 2 pi. And the integrations 0 to 0.001, 0 to pi, E at minus 1000, radius squared, sine of theta, dr, d theta. And something interesting to note, we already know what is this integration. We're integrating sine of theta from 0 to pi, d theta. That integration, yes or yes, will deliver a total of 2. How does it come from? Well, it comes from the identity that tells me that the integration of sine is going to give me Q equals 2 times 10 at minus 9, 2 pi minus cosine of theta, evaluated from 0 to pi, integration to 0, 0.001, E at minus 1000, radius squared, dr. I know this one right here will lead me at 2. If that's the case, we can reduce even more. Q equals 2, 2 times 2 times 2, 8 times 10 at minus 9 pi, integration from 0 to 0.001, E at minus 1000, radius squared, dr. That's going to be my final integration I had to solve. Um, it can be tricky. This integration can be seen as an easy integration since we got an, well, Euler exponential. However, that Euler exponential is paired with a radius square. That means with my variable square. So actually, the best way to go would not be try to solve it by itself. Let's go and call this A, which is any constant. And let's check on integration tables if we got something that we can use. Fortunately, we got integration tables. If we see carefully, this one right here, it's going to be E at AX, X at any power dx. That looks like this one. And this is basically an integral by parts. So we get x, which is r, at 2. That means my m equals 2. If that's the case, we can reduce this to 8 times 10 at minus 9 pi. And the integration becomes x at m, and my m is equal to 2, and my x is actually an r. E at ax, that means E at minus 1000 r over A minus 1000 minus minus M, which is 2, over A, which is minus 1000, integration of x n minus 1. That means r times E at minus 1000 r er. So we reduce everything. However, we still have an integration. Since we still have an integration over there, and we have to keep reducing and reducing, we can actually we could actually go and try to solve it by more integral charts. For example, this one right here now looks like this one, which is integral by parts. Once again, my A is going to be equal to minus 1000. So I can skip this. Let's go and kind of crop it, the one thing that we don't need anymore. Working